on the technology for this stuff, which you've probably kind of been picking up on that. We've been doing a lot on our calculators. So please, if you don't have a calculator and you need to borrow one for your assignments, please do so. Don't feel like you have to do everything by hand. You've talked about scatter diagrams before, probably like in algebra, you did some scatter plots and plotted some points. So in that, your response variable is the variable whose value can be explained by the value of the explanatory or predictor variable. Okay, response is like your y. The explanatory variable is your x. And I think I did print these for you, didn't I? Okay, good. So a scatter diagram is just plotting all these points. So if I wanted a scatter plot for this, I think this is some data that we've seen before. This would be really annoying for us to draw a scatter plot for because my x's go all the way from 35 to 190. You know, my heights are decimals, they're very tiny. So let's use our resources. I want you to enter that into your L1 and L2. All right, so if I want to see what this looks like, I can go to Zoom Stat. It would help if you cleared out anything else that was in there. But we do need to turn on a plot. So if I look right now, my plot is set to the box plot. We want the first one. It's a scatter plot. So it should say your x list is your L1 and your y list is L2.
How did you say a scatter plot was the first
So
one?
second stat plot, go into that, and the very first one is the type we want. It's a scatter plot. So second y equals. So just the same place we go like when we're doing the first. Yeah. So go in there, and then we just need to change this type to the first one here. And it came up your x is L1 here. Alright, did everyone get that? And then if we go to our Zoom 9, we should get a scatter plot.
Okay, so now go to second one. And then plot one. Plot one. On.
No, the first one's the scatter
That one. And then just equal out. Oh, now actually, now go to stack.
Why?
No, don't do that.
Okay.
Go to Zoom. At the top. Zoom 9.
As part of the
There we go. That's fine.
Here's your second step.
I've got it.
So, did everyone get this graph then? What I want, if I ask you to draw these, I am not asking you to really draw much. Basically, put some dots and show me the shape of the data because I want you to do it on the calculator. I'm not going to have you plot these by hand. So really what we're looking at here is, you know, if I were drawing this, you don't have to have any kind of scale. You don't have to really be accurate at all. But I can see it's trending up. It's kind of getting wider as we go up. Just a general showing me the shape of it. That's what we care about. Because the question I'm going to ask you is, what kind of relationship does this have? What kind of correlation? Positive. Why did we say positive? It's going up. Okay, so we can have a positive, we can have a negative. We can have a strong correlation or we can have a weak one. What do you think the difference between a strong and a weak would be?
No, scattered at some points.
I'll
This would
spread
probably be I guess, weak.
Yeah, that's not a great one. So we have a lot of times linear ones, that's what we're going to look at, but we could see other patterns. Right now, if we see something like these, we're just going to say they aren't linear. If we just see a random assortment of points, we could say there is no relationship, okay? If this is linear, So if you look at the scatter plot and it shows the shape of a line, we can find what is called the linear correlation coefficient. Okay, it is denoted by R. And just like everything else, if you ever need to know how to calculate this, where should you go? Formula sheet. It tells you correlation coefficient, R equals, and it has this. We aren't going to do a lot of calculating these by hand. We might work through one or two just to kind of show you how the calculation is done. But it's similar to some of the stuff you did with standard deviation. The value minus the mean. We do it for the x, we do it for the y, so we divide them by their individual standard deviations, multiply them all together, and then add them up. Okay, so it's a lot, and divide by n minus 1. But at least we should recognize what these things are telling me. We know x bar means mean of x. What does s mean? Standard deviation. What's n? The number of points. Okay, so we should be able to read the formula even though it's complicated. But what we need to know from this, it should always give us a number between negative 1 and 1. If it is really close to 1 or negative 1, that indicates a very strong relationship. A positive 1 would be a perfect line going up. A negative 1, what do you think that means?
A line going down.
Perfect decreasing line. If it is close to 0, that means it's not linear. Basically, this number is telling you how linear it is. Positive means it's an increasing relationship, negative tells us decreasing, and then closer to 1 is good. If it's close to 0, there's no relationship.
So would closer to 0 be more scattered,
Yes.
or more curvy like a
It could be
parabola?
either. Basically.
So 0 could be a different shape of line,
Yes.
or
Yeah, it doesn't tell us
Yeah.
if there's a pattern of another sort, just is it a linear
I
pattern.
guess if it was over 0, then it would mean it's a
It's at least increasing.
yeah. So if it was like one of those S, I don't know,
Like a
like a cube,
mm-hmm.
yeah, it's going up.
Yeah, it would still be fairly close to 1. R is not resistant. What does that mean?
Nowhere near, way bigger ways.
Right. If you throw in a really big or a really small value, it's going to change R a lot. Okay, so remember, resistant values are measurements that we can rely on even if our data isn't bell-shaped. If we have bell-shaped data, R is great. If our data isn't bell-shaped, R is going to be less reliable. All right. So this is just kind of showing that this is a perfect linear relationship, so that would be an R of positive 1. On this one, it's 0.9 because we still have a pretty strong relationship. We see it's still positive, but it's getting weaker. That's like a 0.4, negative 1, negative 0.9, negative 0.4. These are both very close to 0 because there's not a linear pattern at all. So I do want to do one by hand just to help us understand how to read the formulas. I do think that is beneficial. So it's a little time consuming, and we are going to partially cheat because in that we have to know the mean of x, standard deviation of x, mean of y, and standard deviation of y. Can we use our calculator to cheat and get those values?
Yes.
Okay, let's do that at least, so we're not doing everything by hand. So you enter both of those and you're going to do your 2 variable statistics. What do you get for your mean of x? Standard deviation. We're doing sample standard deviation.
2.4.
Let's do 449. Okay. Mean of y. And standard deviation of 10? Or so, of y? So you are going to calculate this by hand. We have to do your x minus the mean of x divided by standard deviation of x. And then we're doing the same thing for y. the y value minus the mean of y divided by standard deviation of y. And then we multiply them together. All right, let's kind of divvy this up so we're not all just calculating forever. Selby, I want you to do 1. Mara, you do the 18 on the y. Anna, you've got 3 on the x. Grady, you've got the 13 on the y. Brady, you've got 3 on x. Gianna, 9 on y. Ava, you've got 6 on x. Naren, 6 on y. Natalie, you've got 7 on x. And Abram, you've got the 4 on y. Okay, so you're taking your number, subtracting the mean of your variable, dividing by standard deviation. Okay, Anna.
-0.4083. 403.
Grady.
5.345.
I think it's 0.5345. You've got that. Oh yeah, you said 5. You got it right there. All right, who did I go? Who has the next one? Brady, is that you?
Negative 0.4083.
Gianna? 178 what? Who had the next one? Ava, is that you? 6-7? Okay. Naren?
-0.7130 or 228.
Okay.
Rounded 9.
Natalie? Okay. Abram?
-0.2872.
Are you sure?
That's what I got.
So if we did 4 minus 5.612, or sorry, 4 minus 10 divided by.
Oh, that's why. Wrong one. Alright, let me try it again. -1.0691.
Okay, now what we do is we multiply these. So you take your x times your y, and you get your product. So we get -1.7462. -0.2182. -0.728. -0.5821. And -1.3096. Alright, is this all the calculation? Absolutely. Are we going to do every problem by hand? No. But do we understand our formula so far? Okay, and then the formula says, what does this symbol mean? Yes, we add those up. So I'm going to add that column. And I got -3.7833. And we divide by, looking back at our formula, n minus 1. N here is representing the number of ordered pairs. So how many ordered pairs do we have? So 5 minus 1. So divide by 4. And our R is -0.9458. So what do you think? Is that a pretty good relationship? Yeah, let's double check your scatter plot. if you go to Zoom 9, does it look like a pretty strong relationship? Negative because it's decreasing, it's almost perfect line except for 1 point. So, pretty good relationship there. Alright. Any questions about that? So, if in general, we need to know how to do this on our calculator to help speed the process up. So, we've got all of our data entered. And I may have to change some settings on your calculators. Okay. So, this is a one-time thing. We have to turn something on. Once we turn it on, it'll stay on unless we reset the memory on our calculator. So I need you to hit second and catalog. So second and the 0 button takes you into your catalog. Okay, and we are going to scroll down until we get to the D's. And we want the one that says diagnostic on. So it's like hold on. Now I just crashed my program. It doesn't like all my scrolling. Okay, diagnostic on. Did everybody get there? Okay, I want you to hit enter and hit enter one more time. It'll say done. Okay, you don't have to do this every time. If you ever are trying to get your correlation coefficient on your calculator and it's not showing up, I can help you turn this back on. But now I want you to go to stat, calculate, and we want number 4, the linear regression. It should say x is L1, y is L2. So just enter through that to calculate. And I have different data in my calculator. I didn't put in the data from our set. This was from the previous example. But it should give you an R on that. If it doesn't, that's because the diagnostic isn't on. If your diagnostic isn't turned on, it gives you the equation in A and B, and that's it. So did you guys get something close to negative 0.94 on your calculators? Okay, and that's how we're going to do it 99% of the time. All right. So if we want to check if something is linear enough, okay, 0.9, we're pretty confident that's linear. But if I said like 0.6, is that linear or is it not? There is actually a cutoff for it. So everybody get out your formula sheet. And it's the back of the second page. So second piece of paper, middle it says table 2. And in it, it has critical values. It only gives you the positives because what does the negative mean? Just decreasing. So we're just really looking at the absolute value. But it's based off the number of points in your set. So we had 5 points in our set, right? So you would go down to n equals 5, and it tells you your critical value is 0.878. So anything 0.878 or higher would be considered linear, or negative 0.878 or lower. If you look down, like if you had 30 points, it's only 0.361. Because the more points you have, the more variability we expect anyway, so a smaller number is required. Alright, so that's how we will decide if something is linear or not. So would this one be good enough to be linear? Sorry, the one you guys had? 0.94, yes. Okay, so our answer here, this was example 4. So I would write down from the table the critical value was 0.878. So we had a negative linear relationship since the absolute value of negative 0.94. What was it? 94. The real one on the calculator. Since the absolute value of that is greater than 0.878. That's why we would say it's linear. Okay. Do you have to give me that much of an explanation? No. If on the homework, what I would want, I want you to write down the critical value so I know you looked it up. And then I want you to tell me if there's a linear relationship or not. We could do example 1 too, because that's the one I had entered on my calculator still. In example 1, how many points were there? 12 ordered pairs. So go to your table. What's the critical value when your n is 12? Okay, so that was the data I had entered on my calculator. My R was 0.77. So is there a linear relationship? Yes. Since R was 0.772, is it a positive or a negative linear relationship? Positive, because my R is positive. And since it was bigger than 0.576, we know it's linear. Any questions about that? Here's a question for us to think about. According to data obtained from the Statistical Abstract of the United States, the correlation between the percentage of female population with a bachelor's degree and the percentage of births to unmarried mothers since 1990 is 0.940. Does this mean that a higher percentage of females with bachelor's degree causes a higher percentage of births to unmarried mothers? Does that tell me one thing causes the other? No. You have to be very careful. Is that a good, like a strong linear relationship? Yes. Does it mean one thing causes another? No. All we are able to say is there is some sort of relationship, but we don't know what it is yet. We don't know that one thing's causing another. We just know that they are related. So be very careful in any conclusions that you make. You can't say this caused this. All you are telling me is they are related. All right? We don't have all the information to know why. We kind of have touched on this idea before. We talked about confounding and things that could confuse us. A lurking variable is something that is related to both the explanatory and response that might cause that relationship, but we didn't think about. For example, ice cream sales and crime rates have a very high correlation. So when ice cream sales go up, crime rates go up. Do you think that we should shut down the ice cream shops to help our crime rates? No. What could be a lurking variable that's causing both of those things to increase? Okay. Economy as a whole, maybe. What'd you say, Grady? Sell less ice cream and solve our problems. When do you buy more ice cream? When you run out of ice cream? What about like in the summer? What's happening in the summer? It's hot outside, right? There is a relationship. Crime rates go up when it's hot. Okay. Does that mean that the heat is causing the crime rates? No. But that's a lurking variable. This is explaining why there might be a relationship between those things. Yeah, kids not in school. Maybe that kids aren't in school, they eat more ice cream, crime rates go up. Okay, there are other things, summer vacation, heat, that could be influenced both of these. So be careful about that. All right, last couple slides. Because colas tend to replace healthier beverages, and colas contain caffeine and phosphoric acid, researchers want to know whether cola consumption is associated with a lower bone mineral density in women. The table lists the typical number of cans consumed in a week and neck bone mineral density for a sample of 15 women. All right, this figure is showing me the scatter diagram of it. I went ahead and made it for you. So this shows I did my R and I got a negative 0.06. If I look at my table 2, I had 15 women. What's my critical value when N is 15? 0.514. Alright, so that's bigger than 0.514, so that would tell me there is a linear relationship. It's negative, so it's decreasing. So the more soda you drink, the lower your bone density. So can I conclude that the number of sodas causes a decrease in your bone density? Why are you saying no? What did I just preach to you on the last two slides?
Just because one thing is high doesn't mean
They're related, very much so. We see a clear relationship. But do I know that one thing caused the other? No. Maybe the bone density was lower because you weren't getting enough water. Okay, could that be possible?
Or
Yes.
people that don't, or people that drink more soda on average drink less milk.
Okay, so maybe it's not the soda, it's the absence of another beverage in your diet. So we can't say that one thing caused the other. Okay, so your lurking variables might be other beverages or something like that. Okay, so just be very, very careful. We are not proving something caused another. We're just showing they are related. Any questions? Okay.
So even if it is a real line, then could you
We
say?
can say it's a very strong relationship, but I still
So
don't
if it was
know.
a perfect one, you would say.
How